I don't know if you've heard that, but I've heard that. But it is. Kidney stones are a solubility problem. If you don't drink enough water, the calcium oxalate precipitates out, and you just start getting those little crystals in there. So especially, you could go the calcium route, right, with ice cream and milk, or the chocolate route with the oxalate. Either way, you'll build up and start getting these kidney stones. So the common ion effect. We've already had some of this already, I think, in the homework. Oh, by the way, there is a typo, right, in that handout you guys just turned in. It's that azide anion, CuN3 and 0.2 molar KN3. So the 3 was in the wrong spot, but don't worry about it. That's fine. So how can the common ion effect, how can the solubility of silver 1 hydroxide be decreased through the common ion effect? You want less silver hydroxide to dissolve, right? Christina, how could you do that? You want less, usually you want more to dissolve, but I guess this must be bad stuff. You don't want that much to dissolve. What could you do? Through the common ion effect is pretty much your only choice here. Do we have an idea? What could you do?
You add more base. You add more hydroxide ions.
Add more hydroxide, right? Make the pH go up or down? Up, right? Excellent. Add some more base, right? That's a good one. How about if you wanted the solubility to increase, though, Eric? You want more of that stuff to dissolve. I guess you could, because you had acid that's removing the OH, so it'll leave Le Chatelier. I think that's a good idea. Or, let's see, no, add more silver ions would make it go back, right? So you want to think of it as, you almost pretty much have to write that, how I view it, you pretty much have to write the KSP reaction. And we want solubility to be increased. And KSPs are products over reactants, so you want there to be more products. You want there to be more. Right? So that's where adding the acid would work, because now you're removing this. If you add acid.
That would make solubility increase?
Yeah, because then you're going to Le Chatelier's principle. You're essentially going to be removing the hydroxide. Solubility of silver hydroxide. So if you went through it wouldn't be a very straightforward reaction. It wouldn't be a very straightforward mathematical problem, but it would. Le Chatelier's principle says, hey, you're going to have more product that way, and we're interested in the silver, right? For example, if you have the KSP of lead 2 chloride, 1.7 to the 10 to the negative 5. What's the solubility for this compound? We just took a quiz on this, right? Eustacio, how would you set this up?
Write the KSP.
Yeah, write the KSP reaction. Okay, so what goes on the reactant side? Keep going. Yeah, the lead 2 chloride goes to its, everybody? It's ions, Pb plus 2. And what else? 2 Cl minuses, right? Remember that? Remember the trick to doing this? If they say lead, this is really the charge that goes there, and this is really the charge that goes here. Remember doing that? This is really a plus 2. And since this is a 1, this is really a negative 1. If you don't remember the charges, that's the trick to figuring it all out. You don't remember that stuff. Okay, there's 2 chlorides. And then they want to know solubility. And everybody, the solubility is the what in ice? X. So you got to do that whole gambit. And I don't think we need to go through the whole thing, but that's the story, right? There's nothing there initially. We need to have X and 2X. But anyway, you'd set up this KSP number to equal, what would it be, x times 2x squared? End up solving for your x. Okay. Let's say you, man, Jenny, you're just flying on this exam, right? That's coming up, and you have all this time left on the exam, and you look at your answers to see if they make sense. Like this one, you get an answer. For part A, you get an answer. But for part B, what should happen to your answer? Should it go up or down or not change? Should go up? Careful, right? We're adding, what are we adding? We're adding the chloride. You don't care about the sodium, right? You're adding that chloride. So, and chloride is on the product side.
So if you have more solubility, which way does that shift equilibrium? Like I'm not seeing the relation between solubility and equilibrium.
Everything has to be at equilibrium for you to even talk about solubility.
I mean, like towards products or reactants.
Okay, so if you go back and don't even worry about solubility, just blank it all out. If I add chloride, Cl minus, right? We don't see Cl minus here, but hopefully you do. Because remember that there's only really one solubility rule that I really strongly suggest that you know. And that's that group what? With anything is always group 1. With anything is always completely soluble. So my brain, when I see this, I see sodium ions, which never do anything anywhere, right? But I see this. And if I see this, ooh, there it is. So it's on the product side. That guy's principle, Le Chatelier, says it's going to shift towards reactants. Okay, so it's going to precipitate out the lead. So if it's going towards reactants, would I have less or more product? Less product. And that's how I refer solubility. Is I'm going to have less product. Oh, that's going the opposite direction for solubility, so that means solubility goes down. That's how my brain works.
Yeah, that's what I was thinking too. It's like if it's more soluble, there's going to be a higher.
Has to be more product. Has to be more product. If it's more soluble, has to be more product. Because that's how KSP reaction is always written that way.
So back to that first example, the more is saying that you want more.
You're talking about
Yeah,
this one.
of those two, yeah, because like if when you put more, are you saying you want to add more of that, or that you want more of that?
You're talking about the top one or the second one? The second one. Okay, the second one. I want to increase solubility. So that means I want more product. So one way to get more product, adding silver ion is going to screw things up. Adding hydroxide is going to screw things up. The only choice I have in here is to remove something. And I don't know what I guess I could, if you were really good at your solubility rules, someone could have gave a really good brownie point answer, right? Add, I don't even know what the solubility rules are, but add blah blue that precipitates with silver, right? That would have been a good one. I would have said, ooh. But I like that one. It's a lot easier. Just add some acid, because then you remove hydroxide, a whole shifts.
I didn't see that.
Okay. No, ask, man, because if you don't see it, there's 20 other people in here who don't either. Okay. So what is this? Okay. Now does this make sense? How would you answer this question after all that? Is the answer that you got in A going to go up or is it going to go down? Assuming you had all this time to figure out all this and look at it on the exam, solubility's got to go down because you just added chloride. So you better get a smaller answer for B than you do for A. Right? Remember how to set this up? Let me just set it up quick, right? Just so you remember. PbCl2 solid goes to Pb plus 2 and 2 Cl minuses. Because remember at the beginning of these exams are conceptual stuff, so that could be in there, right? Something like that. Otherwise you have to go through all the work of calculating. You don't have time for that. So now I have numbers to put in the initial row. Do I put a 0.1 or a 0.2 there since I have 2 chlorides? 0.1. The concentration is 0.1, so that's what you put in there. All right? X and 2x, x and 0.1 plus 2x. All right? Remember doing this? Then you got to substitute it all into, what was KSP? 1.7 times 10 to the negative 5. Products over reactants. It's dangerous to skip writing the concentrations in brackets because very often you end up skipping or forgetting to write that 2 squaring. Okay. Then the whole, can we drop the 2x? Yeah, I mean, you should probably go back and check, but yeah, you can.
Are there any where we can?
Yeah, I bet there will
In
be.
Gen Chem we did that, didn't we? There were a few where we had to like work it out.
I think they're, yeah, I bet they're probably in the homework.
Yeah.
Are you going to put quadratic equation on our test?
Yeah, well, I'll give it to you just in case.
Okay.
Do you remember what? B squared minus 4. Those calculators you have, I bet you, if you learned how to use them, I bet you plug in little A, B, and C and it spits it out. I bet it does. I have no clue how to do it though. Okay. So complex ions, kind of interesting. Oh, did you get all that, Daisy? Complex ions, these metals and, you know, things that attach to the metals, they call them ligands. And you can get a number of these different forms that all exist in solution at the same time. And a lot of them they're finding have some pretty interesting properties. But I thought this was really interesting, so I scanned it out of the book. Right? Here's our typical KSP reaction for lead iodide, lead 2 iodide. And what's interesting is if you dump in more iodine, KSP increases. More lead iodide dissolves. Well, that's just the opposite of what we said, right? If you dump in more iodide, dang, solubility is supposed to go down. You're not supposed to get more lead iodide to dissolve. So something really funky is going on. And the really funky thing is look at all these different forms of lead iodide. There's a bunch. So that's where all this lead's going. Okay, it's not going back to lead iodide solid. It's going to all these different forms of complex ions. And each single complex ion, right, has its own, we call it formation constant. Okay? And it's just products over reactants. And they have a number, products over reactants, so it's really not that big a deal. It's just that what's kind of interesting to me is all these, I don't know if you've, what class does this? We have all these equations. You got to solve them all. Probably whatever uses matrices. But what's interesting to me is all these equations are simultaneously valid. So if you know the concentration of, I don't know, iodide, well then that's the exact same number in every single one of these equations. If you know the concentration of, what's another one that's common? Well, the lead 2. If you know its concentration, it goes that same numbers everywhere because all these equations are simultaneously valid. So once you know one, you know it in every single expression. So complex ion formation reactions have tabulated equilibrium constants called, starts with an F, formation constants. And use the symbol, what is that? Is that beta? I think that's beta. I think that's beta. Okay, there's no there should be some Greeks in here that would know that stuff. Complex ion formation, you know, for those fraternity guys. Complex ion formation reactions are always written. Okay, now this is the important one. It's just like KSP. If you do write that KSP reaction flipped around, you're done. You're done for. You can't even start. How do you write complex ion formation reactions? On what side does the complex ion go? Product. You're forming it. To me, the hint is formation constant, right? You're forming it. So the complex ion goes over here, and its ions go over on this side. It's kind of the opposite of KSP. Hey, can the complex ion itself be in the formation constant expression of products over reactants? As long as it doesn't have a, what, subscript? S. Solid or liquid, yeah. It'll be there. Okay. So let's try one of these. And it's just that they get wordy. That's why these problems get ugly. But if you could just write down get to the math and the nitty-gritty, it's not that bad. The cumulative formation constant for tin 2 chloride in 1 molar sodium nitrate is 12. Find the concentration of tin 2 chloride for a solution in which the concentrations of tin and chloride are both somehow fixed at 0.2 molar. So out of all that, what do they want to know?
The concentration of SnCl2.
Concentration of SnCl2. To me, it helps just to do that. I mean, what the heck? Okay. So Shelby, what could we do next? That's what we're after. Yeah, the what equation? Use the word. Use the, what they call it. They call it the formation constant expression. It's like usually before we write the KSP expression, right? But if you can't just jump right to that, you have beta equals 12, right? And that equals, well, products over reactants. It might be easier, since we've never done it before, to write the what first? The reaction, right? So let's ask Mariella to do that for us. What reaction are we? Now we want to know the expression. Shelby's exactly right. Here's our whoever, I think it's Shelby. She's exactly right. So we need the reaction that corresponds with that beta equaling 12. What would you write? Sn plus 2 plus 2Cl minus SnCl2. Okay, now what subscript are you going to put on the SnCl2? What's that? AQ. It's important, right? Because
So we don't assume that's a solid.
the only reason why I know is this. And if it was a solid, it wouldn't be a formation constant expression. It would be a KSP problem. So, okay. Well, it's AQ. It's in the problem. But also, if it was S, it wouldn't be a formation constant problem. I think it would have to be a, if the complex ion formation stops here, that'd be a KSP problem. Okay. So products over reactants. Do I include the tin 2 chloride? Yeah, because it's AQ. And the tin and the chloride, but I got to square it. Okay, man, we are getting there. Brandy, now what? We're getting close. We should have done ice because we're so used to doing ice, right? We should have done ice. I saw the answer, so I kind of led you this way. But if I was you, I probably would have started jumping into ice, right? Let's do ice. Because that's what I bet you're going to do on any exam. You're going to jump and you're going to do ice, which is a very healthy thing. Okay? So what do I have there initially? For the tin, what would you write? 0.2. And then what else? For the chloride, you have 0.2. And the tin 2 chloride? We don't know, right? Now, you want to kind of be careful. When they say it's somehow fixed, that means initially fine. I mean, that's the equilibrium answer, really, right? It's fixed there. It stays there. So these are 0.2 down here, too, because it's fixed. Yeah, technically minus X or something, but no, it's fixed. Somehow they got them fixed.
So the dashes have changed.
I think a healthier way is to put dashes everywhere, because you don't know how it got fixed. So I'd put dashes everywhere until you get to the... To me, that would make the most logical sense, right? But it's up to you. And then, I guess X, right? And X. Okay.
So then you still take this 0.2 on PCl and square root of there is.
Yeah, so see, when I was jumping right to the answer when probably we should have done ice first. But you're going to end up with the same result. It's probably easier to see. We'll solve for tin 2 chloride. We'll substitute in what the equilibrium amounts are. We'll get it. So 12 has to equal, you can put X or tin 2 chloride, 0.2 times 0.2 squared. And you can get it. Okay? Make sense? Let's see. Given the following equilibrium, here's another good conceptual type question. And let's just pretend, oh, let's do this first. Oh no, this is something else. Given the following equilibrium, calculate the concentration of zinc-containing species in a solution saturated with zinc hydroxide solid. Hydroxide's fixed at 3.2 to 10 negative 7 molar. They want, Zach, they want all these, what do they call it? Species, zinc-containing species. Well, which ones are those? If I was going to circle them, what would I be circling here? Yeah, so what would you circle? So would you circle this one? Just starting from top to bottom. He says circle this one. Would you circle this one, everybody?
No. Oh, wait.
All the zinc-containing species. All the zinc-containing species. Everywhere where you see a Z in. Right? Now, there's something wrong with that thinking, though. So what these guys, right? One of those, They're all containing zinc, but one of them, no. You're not supposed to circle. And why? Which one? Don't forget, go back to the very fundamentals of writing equilibrium constant. Whether it's an equilibrium constant, KSP expression, formation constant expression, you always leave out solids and liquid. But why? Their concentrations are constant. They never change. They end up throwing them in with the equilibrium constant or the formation constant or the KSP constant. We don't circle that one. Okay. So the reason why I want to hit on that is how else do you know what you're looking for? Right? So you got to identify what you're looking for. So anything, like someone said, anything containing zinc, except for the guys who aren't changing the concentration, like solids and liquids. It can't be those. Pure solids, pure liquids. Okay, so now we know what we're after. Where would you start? Sochi, where would you start? Well, logically, we only have one tool to work with. Well, we could write ice, but essentially, yeah, but ice would just help us to write the expression. Products over reactants is really all I'm saying is that we have to work with. You can write ice, but then you end up writing products over reactants. So it's kind of like what we did here, just kind of skip the ice thing. If you do products over reactants, let's just pick one, right? I'll start at the top and work our way down. So if you did products over reactants, KSP has to be 3 times 10 to the negative 16. Products over reactants, you'd write what, Victoria? Concentration of the zinc 2 plus. And you got to square it all over 1. Okay. Well, what other information did they? We can write the expression for every single one of these. But notice, right now we have one of our answers. Can you see it? We know the hydroxide. Good. Eric saw it. We know the hydroxide. So then now we know the zinc, right? Plug in 3.2 times 10 to the negative 7. You got to square it. Divide it into 3 times 10 to the negative 16. And we already have the zinc. About 2.93 times 10 to the negative 3. Okay. So why did we pretty much, it looked like a really ugly question, but pretty much we just do the only thing we know how to do, and that's write the expression. Because once they give you these constants, you have to use them. That's just products over reactants. We'll have to do that for every single one of these. And I probably wouldn't jump down to number 4. I would probably do number 2 next. Right? Because I bet you it's going to be one equation with one unknown. Because now we know the zinc, we know the hydroxide, and then we'll solve for that one.
So the zinc stays the same throughout, right?
Because they're all simultaneous equations. They're all equally valid. It doesn't matter where you start. You could have started anywhere in here, and you'd end up with the same answers. Okay? So that's, I mean, there's some work here to do, but I think you see what to do, right? Jamie, you see what to do? What would you do next? Yeah, well, where would you go next? So now we have the zinc done. Yes, good word. Write the formation expression. Beta 1. Exactly. Put the answer you got for zinc in. Products over reactants. She's exactly right. Just to make sure everyone's agreeing here. All right, and then you just plug in the zinc and the hydroxide and solve for that, I don't know how you would call that, zinc hydroxide complex. I'm not sure how you'd name that. Make sense? Okay. This question. Let's say, see if you guys are following. Jessica, if you can see the insight into this question, let's see if you can see it. If you had the power to cross something out on here and make this a much, where's Jessica? Where'd she go? If you had the power to cross something out on this question and make it a much easier question, what could you cross out? What could you cross out? I don't know if you see what I'm driving at. Does anybody see what I'm driving at? It's your quiz. You had the power. What would you cross out? Just delete something. This. Daisy said it. Cross that out. Why? You're interested in what order anions will precipitate, right? So you have all these solutions in there. Somehow, something's going to precipitate out first, right? Second, third. It's just the guy with the highest solubility, in this language would precipitate first or last? He's so soluble, right? He's not going to precipitate. So the guys that are really, really low solubility will precipitate out first. So you could, by taking out that bottom one, all you need to do is look at what? The KSPs. What we're interested in, really, what we're interested in is the X. We're interested in the solubility. But why go through all the work if everything is in the format of KSP equals x squared, right? If you did all of these, this equals x squared, this equals x squared, this equals x squared, right? Why go through and take the square root of every one of those? Just look at the KSPs. The exact same format. You get the exact same answer of which solubility would be the biggest, which would be the smallest, right? So in order they would precipitate, would it go from, right? Highest solubility would be last. I got to write it over here.
Biggest numerical exponent.
High solubility. Oh, how do you spell solubility? That's close enough, right? Lowest solubility. So that's the order that they would precipitate out in. Precipitate. So what would be first? If we can cross out this bottom one, what would be first?
AgI.
Silver iodide? Everybody agree? Man, look at his solubility. I mean, he's so low, hardly anything is in there, and he's going to be a precipitate already. Silver iodide. Then what? Then what? Silver bromide, and then silver chloride. Okay. By throwing in that bottom one, though, do you see how ugly of a question it makes it? Now you can't compare KSPs. You can't do that little trick, that little shortcut. You have to actually compare what you're supposed to be comparing in the first place, which is what? The X. X is the solubility. Sorry. Solubility is the X in ice. So you got to write them all out. You have to. You have to compare the X's. Okay?
So then would it just swap for that last X?
So you're going to have to find X for every single one of these. You're going to find the solubility for every single one of those. Okay, let's try it. Try it. Because the first three aren't so bad. You don't need to write ice for all that stuff. You might even be able to see it and write the KSP expression. Right? So go ahead. All right. So pretty much just find the square root of each one of these.
So when they give you a KSP, you assume that that first thing is a solid, right?
Yeah, you have to, because it's the only thing that makes sense. It can only be KSPs of solids. So take the square root of these first three and get your solubilities. But the last one, you're going to have a little expression to write. Well, no, now we don't, if we didn't have that last question, that silver chromate, this works. But now that we have silver chromate, we can't compare KSPs. We have to compare X's. So this relative order is right, but where does the silver chromate go? So you don't know unless you calculate X for everything. Man, I hate skipping ice because I so often screw up. It takes 5 seconds to write ice. It's very often worth it. I think that's right though. 2x and x. You got to square the 2x and the x. Right? About 6.8 times 10 to the negative 5. I got 6.8 times 10 to the negative 5. Hopefully somebody else got that. For the solubility for silver chromate. Anybody else get that?
Oh, I forgot.
All right. Did you? Oh, good. Whew. Okay.
Nice, and you're putting in the 2. You put 2 in on the tantrum.
Yeah. Yeah, if it has a stoichiometric coefficient.
So the number of people with the angle, or the number of equilibrium. I guess it's
It's not worth skipping writing. You should really write that. Right? Oh no!
I was gonna say, so don't we add that to the ice?
Oh shoot. Nah, we do, don't we? Oh man, this is a lot more work than I thought it was.
But it's all over.
They're all point ones.
But all the exponents are bigger than negative 5, right? So,
Yeah.
but it doesn't matter at the end.
So then that just means that we drop the x's, but the point ones are gonna stay.
Oh, that's right.
That now everything's messed up. Ah, you are so good. You guys are so right. Shoot, I thought I was going so good here.
So if it had given a polarity, then we always.
Yeah, so we gotta put it in. I didn't see those stupid numbers. I should erase that. That's the number you should have erased. All right, so we have 0.1 plus x. I think in the end you'll end up at the same result where it's at, but we should do it right.
Is there a time that we can just look at that and know?
Yes, that's the point of doing the first way. You just look at it when they all have the same chemical formula ratios. Like they're all 1 to 1. They're all 2 to 2. They're all. So then the KSP expression will be identical. So without this last one, we could have just looked at it and had our answer and we would have been done.
So you disregard the
Wait a minute, we were close. We didn't do it quite all wrong, right?
Shelby, it's all wrong the right side.
So we'll have 4x squared times 0.1. Yeah, and drop our x.
Will that 0.1 no have any effect on?
Yeah, we have to put it in all of them. But I think Javier's right that in the end,
So the same order.
we should have the same order.
It should be the same order but different solubilities.
Yeah. 5.5 times 10 negative 7.
Oh, he was just saying if that weren't there, then it would be really fast. Because they would all be squared. But he was just saying, like, I wrote it like this.
Oh, because it has a
Right. He didn't actually drop that. He was we're still using that problem. He was
Oh.
just saying, if we remove this, if this was removed, then it's much simpler because since they're all
But this one you have to calculate it out.
right. Well, because exactly. Because there's two ways here. When you have like all the same.
All you do is divide those all by 0.1, right? 10 negative 9, 5 times 10 negative 12. All you do is divide them all by 0.1.
Once you understand like how everything fits together.
Okay. So where does it go then? It should go 10 negative 7. It's the highest. It would go way over here. Make sense? It'd be the highest. And we made that as complicated as we could possibly make it. All right, so have a good day.